Chapter 15, Solutions. Okay, this is probably one of the most applicable chapters to everyday chemistry. Okay, this is one of the most applicable chapters to everyday chemistry. Solutions. What's the majority of your body?
Water.
Water. So that means everything that's in that water is in a solution. Right? That hydrochloric acid we did our lab with, that was a solution. We rarely play with pure hydrochloric or any pure substances. Everything's in mixtures, compounds, solutions. So what is a solution? It is a homogeneous mixture. It is a homogeneous mixture. So that means when we have a solvent and the solutes, they're mixed completely inside of whatever container. Does this look similar to some of our gas stuff? From the gases, remember one of the sort of gas assumptions was it's a mixture that is evenly distributed in a container, right? Just like here, in solutions. It is a homogeneous mixture, meaning if we take a little bit of a mixture from the top, it is the same concentration as from the bottom. It is evenly spread out. Our solute is evenly spread out in the solvent. So the solvent, we define it as the substance that is present in the largest amount. Present in the largest amount. So in our hydrochloric acid that we used in our lab, what was present in the largest amount? Water or HCl? Water, right? We dilute that HCl in the water. So solutes. That is any other substance. The solute is any other substance that goes in the solution. In the aqueous solution, that is probably the most common solution you'll ever see. The aqueous solution means it is just with water. So we have HCl in water. Or, what do you guys think is our probably other most common solution? Salt in water. So probably our most common here is salt. Solubility of an ionic substance. So salt, NaCl, what type of bond is that? Good. It's an ionic bond. What do we have to make up an ionic bond? What is it, Jack? Good. A metal and a non-metal. So this is we put salt in the water. You have these little salt crystals. You put them in the water. You don't see those salt crystals anymore, right? They dissolve. So our salt, the NaCl, is separating into its ions. Na plus and Cl minus. Why is Cl minus bigger than Na plus? So our chlorine, typically that has 17 electrons, right? Now, Cl minus, that has 18 electrons. It's got more electrons. It means the ratio of protons to electrons is no longer 1-to-1. So now that electron isn't being held in as tight. You guys remember this a little bit? Yeah. Now sodium, Na plus. That means we've lost an electron. So sodium has 11 protons and now 10 electrons. So it can hold those 10 electrons much tighter. So that's how we get that size. And now specifically we can look at how water interacts with this at a molecular level. We can see the salt crystals dissolving, but we want to know what happens on a molecular level. So we have here on the green and silver, silver, that's a salt crystal. We have our sodiums and our chlorines. Now if you remember, our water has a dipole moment, right? Water has a dipole moment. So now the positive end of our water molecule, what ion does that interact with? The negative, or the chlorine, the Cl minus. So our positive end is going to interact with our Cl minus, and you can see that up in the top here. We have our polar water interacting with our ions of the sodium and chlorine. So now We don't have to have ions, though, for water to interact. We can have polar compounds. So right here we have ethanol. This is ethanol. What part of the ethanol compound is polar? Good, the OH bond right here. That OH bond is polar. And that is what is going to interact with our water. So you look here on the right, we have our ethanol, the partial positive side, and then the partial negative side of our water molecule. That is interacting. And that's how ethanol is soluble in water. What does it look like if something is not soluble in water? So right here, this is insoluble in water. We're looking here at oil and water. So here's oil and water. Oil, what it looks like, we're just going to draw a shorthand notation. It's a long hydrocarbon chain. So it looks like that, where at every corner there's a carbon with two hydrogens. So it's non-polar. Now water, that's a polar molecule, and since the other is non-polar, they're not really going to interact. You're going to get two distinct lines here. So those hydrogen bonds in the water molecule are going to keep all the water together, and then that oil, all that London dispersion is going to hold that oil together. But because London dispersion is so weak, it doesn't interact with the hydrogen. So now we want to look down again, go back to that structure in the picture of that sodium, the sodium crystal, so the Na and the Cl, and how do we actually dissolve something? So right here what it is that water molecule gets inside of the hole. So you have your Cl minus and then your sodium ion. Remember you had a sort of like a structure like this? The little guys and the big? Yes? Well, this water is going to come in and attack right inside here, right between. It's going to get in there and disrupt those forces. So it goes into that hole. Now, water interacts with itself already, right? Yeah, it has hydrogen bonds and has a dipole moment that interacts with itself. So what has to happen is it has to create a hole in itself also. And that Na and the Cl, those ions are also going to attack between water molecules. So these are going to attack between water molecules. And this is where we get the term like dissolves like. Like dissolves like, meaning if we have a polar solvent and a polar solute, they will dissolve. Two nonpolars, so a nonpolar solvent and a nonpolar solute, will dissolve. A polar solvent and a nonpolar solute will not dissolve. It's like oil and water. Good. Yeah. Oil is nonpolar and water is polar, so they will not mix or dissolve. Take a look at this question now. Answer this question. First one. Will carbon tetrafluoride mix with water? No. Why? So we're going to say no. Now NH3 mix with water? Yes. Why? Good. CH3OH. Methanol and water. Yes? Good. And then N2 and methane. Yeah, good. Why does that one work? Good. Two, they're both non-polar. And also, if you take a look, those are both gases, right? N2 and CH4, those are both gases. And what's an assumption about gases in a container? They evenly mix. Good. So here we go. Solubility. Now this is where we're talking about saturation. Now if you, I don't know if you guys have done this for fun at all, but if you've ever been out with your buddies to a restaurant, and I know Connor's done this, try to pour like salt or sugar in your buddy's drink when they go to the bathroom or something. to try and make it taste bad. And if you put salt or sugar in somebody's drink, and then you mix it up, some of it disappears, right?
Yes.
Yeah, it dissolves. But as you continue to add some salt or sugar, all of a sudden you notice you get like a little pile of salt or sugar crystals on the bottom of their drink, and then they come back and they see it, right? Yep, exactly. What that's called is that's a saturated solution. That means we have put as much solute as that solvent can hold. So you're putting salt, 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 and it's dissolving, and then there's a certain point that as you keep adding salt, it can no longer dissolve because all those water molecules are busy breaking up other salt. So saturated means you can't dissolve any more solute. So then what do you think unsaturated solution means?
You haven't reached the limit.
Yeah. You haven't reached the limit, so you can add more. But take a look at saturated solution for a second. Take a look at saturated solution. Right here it says, at that temperature. What that means is, do you think solubility is dependent on temperature? Oh yeah. Meaning, what does temperature do to those water molecules? When you add heat to the water, those water molecules start to move around a lot faster. So they can get in between that sodium and the chlorines a lot faster and a lot better. But as you cool that solution down, it can't get in there as well. So then you're not going to be able to put in as much. Does that make sense, Jackson? So if I put a bunch of salt in at water at a high temperature, and then I cool that water down, what do you guys think is going to happen? Well, it's going to be super saturated for a little bit, but then what happens? Good, the salt will then fall out of solution, and it'll be what's called the precipitate forms. So now we just talked about this, a supersaturated solution. This means we have a solution at an elevated temperature that we're able to, say, dissolve salt in. But as we cool it, it now contains a lot more dissolved salt than what there should be.
Why doesn't it just come back out?
It needs sort of, here it says you need a sort of a catalyst, or you need to disturb it. Because everything's in sort of harmony, just floating in that solution as it cools. And then as soon as you disturb that, you they call it etch the glass a bit, so you take a little spatula and sort of scratch the bottom of the glass, and then you'll start stuff to see crash out, because you've disturbed. Yeah, it wouldn't take much. Wouldn't take much, but you have to disturb those molecules, and then it'll start to crash out. So a supersaturated solution is when a solution is saturated at an elevated temperature. So solutions are mixtures. Right, we just went over that, we agreed on that. Solutions are mixtures. Now, we can change the amount of stuff in our solutions, right? We can put, say, a teaspoon of salt in our water, a tablespoon of salt, a little teaspoon of sugar to help the medicine go down. We can change our amounts. So we need to know the amounts of the solvents and the solute. So we need to know how much, say, water is in our container and how much sugar or salt we are putting in our container. And we can do qualitative measures of concentration. So concentrated, what's that mean? If we have something that's very concentrated, there's a lot of it, right? There's a large amount. And if we have something that's dilute, we don't have that much. So a concentrated solution means we have a large amount of solvent or solute. A concentrated solution means we have a large amount of solvent or solute. You tell me. Sol what? Solute. Good. Concentrated means we have a lot of solute. So dilute means we have a lot of what? Solvent. Because we have very little. So here we go. Mass percent. Now we're getting into numbers. Mass percent. So this is the mass of solute divided by mass of solution. Now, what do you think the mass of solution consists of? Solute and solvent. Okay, so our mass of solution, solute plus solvent. It's so important, it's written twice. I just wrote it, and it's right below it. So the mass of the solute plus the mass of the solvent is the mass of the solution. You might be tempted, though, to do mass of solute divided by mass of solvent, but that's something different. Okay? You want mass of solute divided by mass of solution. Okay? And then you just multiply by 100 to get the percent. Give this a shot. They gave this to you in masses to start with, so it should be pretty easy. Answer, 6.6. 6.6%. So you just take your grams of solute, the glucose, divided by glucose plus water times 100, and you get your mass percent. All right, the next one. This is what you're going to use the most often. This is what you're going to use most often. This is what you see in labs. Molarity. Okay, moles per liter. So that is our moles of solute per liter of solution. So in a 2 molar solution of hydrochloric acid, what's that mean? 2 moles of what? HCl per liter of water in a 2 molar solution. So if I give you a 2 molar solution, if I have 2 molar solution, and I measure out, say 100 milliliters, can you tell me how many moles of HCl there are in it? Yeah. So if I have a 3 molar HCl, I can have 6 moles of HCl per 2 liters, or 3 moles of HCl per 1 liter. Calculate, you have 1 moles of sugar in 125 mils of solution. What is the concentration in molarity? The answer is 8. Is an 8 molar solution. And how we do that is we just take our moles per liter. But remember, it's moles per liter, so you need to convert milliliters to liters. Okay? So just remember, there's 1,000 milliliters in 1 liter. Okay, does everybody get that? 1,000 milliliters in 1 liter. Any questions on that? 500 grams of potassium phosphate is dissolved in enough water to make 1.5 liters of solution. What is the molarity? Answer. 1.57. 1.57. What is, taking notice, potassium phosphate is K3PO4. Okay? So you had to get the molar mass. And then you just divide by the 1 liter after you have moles to get your molarity, which is 1.57. This is tying everything in from first semester and all that, right? Naming compounds. So K3PO4, use the molar mass to go to moles. Any questions? Now, try this one. Now you're trying to go another direction. What volume of this solution do you need to have 2 moles? 200 milliliters or 0.2 liters. So all you had to do was solve around for liters. So if you started with moles per liter. You started with moles per liter. Do the molarity. You can solve for liters. So it's just moles per molarity equals liters. So first thing, dilution. This is probably one of the most important things you're going to use in this chapter is this equation. M1V1 equals M2V2. The capital M stands for molarity, and capital V stands for volume. For volume, do they both have to be in liters? Do they have to be in liters? The answer is you must have the same. So if V1 is in milliliters, V2 must be in milliliters. If V1 is in liters, V2 must be in liters. So dilution is the process of taking water and adding it to a concentrated or stock solution. And what you do is you're adding water to the solution to get to a desired concentration. That equation, M1V1 equals M2V2, lets you calculate any sort of dilution. So what you would do is here's sort of like your method. You have a volumetric flask with water at the bottom, and then you're going to take your stock solution in a pipette, and then you add it to the water. And then you're going to just give it a little swirl, and then dilute it to the mark. Now when you do M1V1, what you're actually doing, do this question. Use that equation we just talked about. Answer is 0.06 liters or
60 milliliters.
60 milliliters. So when you set it up as M1V1 equals M2V2, your M1 is 2 molar, and you need your volume you don't know. Your M2 is 0.800, and your V2 is 150.0 milliliters. Now your answer is going to be in milliliters because you put milliliters as your V2.